This is section 11.6, part 3, and we'll turn from differentiating vector-valued functions to integrating vector-valued functions. Once again, it's as simple as doing each component separately. So if I wanted to integrate this vector-valued function in 2 dimensions, I would simply integrate the first one, and I'm going to get here. I'm going to write out this first U substitution. My guess is most of you are doing these in your head right now, but I'll write the first one out just to be sure. If we had U equal 4t, du would be 4 dt, and 1/4 du is equal to dt. So I'd have the integral of e to the u, and then instead of the dt, I'd have 1/4 du. So I get 1/4 e to the u, which is actually 4t, times I. Plus, same idea here, right? Technically, you'd be letting u be 7t. So instead of a 1/4, you'd get a 1/7 here. If it helps you to write it out, by all means do so, but I'll usually do those little U substitutions that just result in constants. I'll usually do those mentally. So in this case, we'll get a 1/7. And then the integral of cosine is sine of 7t in this case. And that's our j component. And then as it remarks up here, keep in mind that your constant of integration is actually going to be a vector when we're integrating a vector. So I'm going to have a plus c as a vector c. And there's my antiderivative. Let's do another one. Let's see here. I'm going to rewrite this one. That's 3 times 1 over t. Most of us recognize 1 over t as the natural log, is the antiderivative there. And then I'm going to write that as 4t to the negative 2 for j, and 8t to the negative 3 for k. So I do get 3 natural log t for I, and that'll become a 4t to the negative 1st over negative 1 for j, and an 8t to the negative 2nd over negative 2 for k. And again, my constant of integration has to be a vector. So I end up with 3 natural log t I minus 4 over t j minus 4 over t squared k plus c. All right, other than just standard U substitutions, the only other type of integral that I will expect you to do by hand in this class is the occasional integration by parts. Other than that, all of the fancy integration techniques that you probably learned in Calc 2, partial fractions and trig substitutions and all that good stuff, we will actually generally use technology to do. So in case you were worried that you'd forgotten some of those, no worries. I'm not going to hold you responsible for those, with the exception of the occasional integration by parts. So that said, let's do a quick review of a situation where integration by parts is necessary. All right, so here we go. In this problem, it's actually the very first one that's going to require integration by parts. Typically, when you've got a product that's not just a standard integral, integrating by parts is a good way to go. So to do this one, I'm just going to remind you, integration by parts looks like this. The integral of u dv equals uv minus the integral of v du. In this case, I'm going to let u be t, and I'm going to let dv be the e to the t dt. du then is just 1 dt, and if I integrate both sides here, The integral of e to the t is still e to the t. So I'm going to get uv t e to the t minus the integral of v du would be e to the t dt. And the integral of e to the t is still e to the t. So I just get t e to the t minus e to the t. So that's going to take care of this first term. The second term is just a standard antiderivative. That's your arctangent. So in this case, arctangent of t. And then this third one, I'm going to notice that the derivative of the denominator is actually the numerator. So I think I'm going to want to use substitution on that one. Let's go ahead and write it out because it's more than just a constant. If I let u be the denominator, then du would be 2t dt, and 1/2 du is equal to t dt. So in my integral, I have a u here in the denominator, and then this t dt becomes a 1/2 du, so I'll make that a 1 over u, giving me 1/2 natural log u, or in this case 1/2 natural log of 1 plus t squared. I dropped the absolute values since 1 plus t squared is positive anyway. So that's going to be my z component. And then I'll add my constant of integration, and I'm good to go. So again, primarily there are a few problems just to review some of those techniques of integration that you may not have thought about for a little while. All right, in example 10, we have an actually not an antiderivative, we have a definite integral, right, from 1 to 4. So we're just going to use our fundamental theorem of calculus to evaluate this, just like we would have done back in Calc 1. I'll start by getting the antiderivative, which would be 6t cubed over 3 for I, plus 8t to the 4th over 4 for j, plus 9t cubed over 3 for k. And I won't bother with the plus c this time because I've got limits of integration from 1 to 4. Simplifying just a little bit, 2t cubed I plus 2t to the 4th j plus 3t cubed k, evaluated from 1 to 4. And just like we did before, we always plug in our top limit first. So that's going to be 2 times 4 cubed I plus 2 times 4 to the 4th j plus 3 times 4 cubed k. And then we subtract what we get when we plug in the lower limit of integration. That's just a 1, so that one's simple. 2i plus 2j plus 3k. And then there's nothing left to do other than a bit of arithmetic. Let's see, 2 times 64, that'd be 128. So 128 minus 2 is going to give me 126i. 2 times 256, that'd be 512. So 512 minus 2 gives me 510j. And 3 times 64, is that 192? Yeah, 192. Minus 3 is going to give me a 189k. So definite integrals, again, work out very similar to what you're used to from Calc 1. All right, last example for this section. Solving for the plus c is sometimes possible in the case that we're given an r prime, missing an arrow there, And I'm also given what's called an initial condition on the r. In other words, I know a specific value of r. I can use this initial condition to solve for the c. So let's start by finding the general form of r. If I know r prime, then r is going to be the integral of r prime. So let's see here. The integral of t to the 1/2 would be t to the 3/2. Dividing by 3/2 is the same as multiplying by t 2/3. The integral of negative sine is actually positive cosine. And we had a multiplier of pi, but I'm going to end up dividing by pi because of the little U substitution I get there, so those will actually cancel out. And then this is really 3 over t, so that's going to give me a 3 natural log t. Plus c. All right. I now know that when t equals 1, r is equal to 1, 1, 1. So if I plug in all of that information, r is 1, 1, 1, and t equals 1. Like so, I can now solve for that constant. So inside my vector, 2/3 times 1 is still 2/3. The cosine of pi is -1. And the natural log of 1 is 0. So if I simply get rid of this vector by adding a -2/3, a +1, and a 0 to both sides, I'm going to get 1/3, 2, 1 as my value of c. And if I plug that back in here, I can now write a form of r of t that does not have an unknown c value. So I already had 2/3 t to the 3/2, cosine pi t, 3 natural log t, plus what I now know is the c, 1/3, 2, 1. And it's always nice to do the arithmetic and get a combined form, so I end up with just 2/3 t to the 3/2 plus a third, cosine pi t plus 2, and 3 natural log t plus 1. All right, that brings us to the end of section 11.6.